Disubstituted cyclohexanes, cis and trans. We've discussed cis and trans, and we talked about how cis and trans mean those substituents are on opposite sides of the ring if they are trans, or if they're on the same side of the ring, that they would be called cis. So if you could imagine which of these would be on the opposite sides, which of these would have the substituents on opposite sides, and which of these would have it on the same side. Might have guessed it correctly. Yes, this is trans. And again, the reason why is because you have these groups are on opposite sides. This chlorine is coming out towards you, and this methyl is going away from you. That's what the hatched line means. So groups on opposite sides of ring. Here, this is cis because both are on the same side. They're both coming out towards you. So this is cis. Again, groups on same side. Not sure what's happening here. Same side of ring. Now, you might have think that these are flipping back and forth. Nope, there is no equilibrium between them, because again, there's a restricted rotation around this CC bond. So there's no interconversion between them. Now, as a skill, you need to be able to draw this. Do your best. Of course, we're not expecting perfection here, but do your best in actually drawing the chair conformation. Now, again, you're going to have to pardon me here drawing it, because it's not as easy as using pencil and paper, but we will do our best. So you need to draw two parallel lines. Like I said, I'm going to do my best. And then what you need to do is connect one end, extend it, and then connect them right here. Again, not the perfect. Nope, let's go back. Again, making a mistake because it is not actually feasible or as easy to do it on this computer versus the pencil. I would have done it very quickly using the pencil. So here it is. There we go. Finally, there it is. That's a chair conformation. So two parallel lines, you extend them, one at an angle, the top one, other one at an angle going up, and then you connect the ends. So you're going to need to remember, where are the axial, where are the equatorial? So we will right away talk about the axial. Now, an easy way of remembering the axial hydrogens or the axial bonds is to actually think about this ring right here. So this ring tells you that when it's pointing up, it means the axial is pointing up. So here it is. This is pointing up. If it's pointing down, then the axial is pointing down. The axial is pointing down. The ones in the middle are a little bit tricky. You don't have to do them like the textbook, where they go and they break the bond. That's kind of professional drawing. You can put them in the middle. It's okay, like this. So if it's pointing up, it's up. If it's pointing down, then it's down like that. So these are the H's, let's say. I put the H's, but as just to show you, but we would need to remember the locations again of these axial bonds. So here are your 6 axial bonds. Now, where are the equatorial? That's the question. Well, the equatorial, those are a little bit, they require a little bit of memory, but they, again, you need to remember that Mercedes sign, remember, for the Newman projection. So this one would be at an angle like this. Here's the equatorial. This one would not be down because it would not make the, remember this right here. Oh, not really. If you remember this, remember, these are kind of the angles that you need to have. So this would be kind of along that angle like there. And this one would be also along that. This one would be down. This one would be in the back like there at an angle. Has to be at an angle. And of course, this one would be at an angle like that. So these are your equatorial. The red is equatorial. And the blue is axial. So this is, you should train yourself on doing that. And of course, if you can do it, I can give you the templates, but you would have to put the axial